I'm Julen Agirre from the University of Mondragon, and I'm going to present a summary of my PhD project for the DYMAT conference entitled The Development of a Thermomechanical Tester for Intermediate Strain Rates and Phenomenological Modeling of Microstructural Evolution, an application to hot forging of Inconel 625. So this is the outline I will follow during the presentation. First, I will introduce the topic. Then I will present the development of the automatic thermomechanical tester we developed. Then the Inconel 625 experimental characterization and modeling, and finally, the industrial case study and conclusion. Getting into the topic, nickel-based superalloys are materials that are employed in environments in which corrosive environments, high stresses, and extremely high and low temperatures are involved. So applications could be the aeronautics, oil and gas, wind power, or nuclear power energy applications. The components for these industries are often manufactured by the hot forging process. And what's the hot forging process? So it consists of starting with a simple geometry by compressing between two dies, obtaining a more complex geometry. So the benefits of this manufacturing process are that near-net shape components can be obtained with a high productivity and with outstanding mechanical properties. So which is the problem when forging nickel-based superalloys? That due to their high resistance at high temperatures and also the high cost of the material, so their forging process it's getting more complex. So finite element simulations are widely employed for designing processes and also for optimizing them. We all know that the accuracy of finite element simulations is directly linked to the accuracy of input parameters. And in hot forging process simulations, there are three main groups of inputs to introduce. On the one hand, the process parameters, the material parameters, and finally, the part-die interaction parameters. In my PhD, I focus in the material parameter characterization, focusing on the flow stress and also in the microstructural evolution. So depending on the forging parameters, we can obtain a fine grain structure or a coarse grain structure. In general, if we want to obtain good mechanical properties, we need a fine grain structure, and especially with Inconel 625, which is a material not designed to strengthen it after the forging process with a heat treatment. So it's important to get a good microstructure from the process itself. So in the forging processes, the main phenomena that govern the microstructural evolution are the grain growth and the recrystallization phenomena. Let me introduce briefly this phenomena. Static grain growth occurs when you hold the material at high temperature. Dynamic recrystallization occurs when you deform the material at high temperature. So you start with a coarse grain size and you refine it during deformation. And there's a third phenomena called post-dynamic recrystallization that occurs when you deform the material without reaching full recrystallization and you hold it at high temperature. So recrystallization phenomena influenced by three parameters mainly: temperature, strain level, and strain rate. And in forging processes, the strain rate is directly linked to the type of machine you use for the process. In the figure presented by Prasad, you can see the strain rate ranges depending on the forging facility you are using. And I will focus in the hammer forging, which is the least expensive technology. It's the most versatile one, and the intermediate strain rate range is ranging from 10 up to 200 or more. Here you can see a video provided by Ulma Forging Company when you can see a big speed blows. So as I said, it's really important to characterize materials for the process conditions. So for the lowest strain rate range, the conventional servo-hydraulic machines are used. For the higher strain rate range, split Hopkinson pressure bars are utilized. And there's a gap in between in which very few facilities exist to characterize materials, especially if you want to test at high temperature and also at high strain levels, which are involved in forging processes. So the objectives of my PhD were, on the one hand, to develop a thermomechanical tester for testing at intermediate strain rates and also at high temperatures, to experimentally characterize Inconel 625 under hammer forging conditions, calibrate microstructural models, and then validate test its validity in an industrial forging environment. Let me present the automatic thermomechanical tester we developed through my PhD from zero. This machine, it's a fully automated thermomechanical simulator capable of reproducing diverse forging and, in general, forming conditions at laboratory scale, and it consists of a principal furnace, an isothermal hydraulic press for low strain rate testing, and the direct impact drop hammer, which is the main novelty of the machine we developed for intermediate strain rate testing, with strain rates up to 100 or even more. So we have in the right-hand side the isothermal hydraulic press for low strain rate testing, and then the hammer, which is a weight pushed by a high-pressure pneumatic cylinder, and data acquisition in this case is carried out by a high-speed camera with digital image correlation, and the force is measured by a piezoelectric force sensor attached to an oscilloscope. So here you can see a video of a uniaxial compression test recorded by our high-speed camera. Now I will show how this machine works with this video. And yeah, as you can see, the machine is fully automated, which increases repeatability. So it picks the sample, it moves to the principal furnace for heating to the testing temperature, and then it automatically moves to the testing position. In this case, to the isothermal hydraulic press for low strain rate testing. Yeah, and after the test is completed, the sample is quenched in water to freeze the microstructure to characterize dynamic recrystallization kinematics. And the same for the hammer test. We pick the sample from the initial position, we move it to the principal furnace to heat it up, and then we move rapidly to the testing position for the high-speed hammer blow. Yeah, so after the development of the machine, we had to validate it, and for that, a validity campaign was carried out in collaboration with NTNU in Norway, in which uniaxial compression tests of an structural steel were performed. Then numerical Johnson-Cook hardening models were calibrated using independently hammer data and Hopkinson data, and the experimental and numerical results were compared. So here you can see the engineering stress strain curves at different velocities in the hammer and the Hopkinson pressure bar. Yeah, interestingly, we see that in the tests in the direct impact drop hammer, we reach a high strain level even at intermediate strain rates. So here you can see the results, the comparison between the experimental data and the numerical data of both models, in which a very good agreement was observed. This way, we concluded that the machine we developed was able to characterize material at intermediate strain rate. This can be seen in detail in the paper we published in the International Journal of Impact Engineering. So after the development, we started characterizing the Inconel 625 nickel-based superalloy. First of all, we characterized the hardening, 3 temperatures, 950, 1050, and 1150 at 3 low strain rates, so 0.1, 1, and 10. And then in our direct hammer, also at the 3 set temperatures, 950, 1050, 1150. These curves are really interesting because we achieved to characterize the material at high temperatures and also at intermediate strain rates with a relatively constant macroscopic strain rate evolution. So here you can see the curves we obtained. So 3 temperatures and 4 strain rates. And after characterizing the hardening, we jump to the dynamic recrystallization characterization. That uniaxial compression tests were performed at the same 3 temperatures and at 4 strain rates. And in this case, we stopped the test at different strain levels in order to characterize the kinematics of dynamic recrystallization. So after the test, we quenched fast the samples and we prepared them for microstructural analysis in the EVSD. Here you can see the illustration seeing how dynamic recrystallization fraction increases with strain level. In this picture, you can see a classical tendency of dynamic recrystallization with higher recrystallized fractions and bigger recrystallized grain sizes with higher temperature. And the recrystallized fraction, or so recrystallized grain size, has a constant evolution with strain level. The same with the hammer tests at intermediate strain rates. In this case, we observed a really high recrystallized fraction evolution, and we attributed this to the high adiabatic heating that we observed at these intermediate strain rates. The same in the recrystallized grain size, and in this case, we observed an unusual evolution in terms of a strain level that wasn't observed previously in literature, due to the few facilities that exist to test samples at these under these conditions. So after the experimental campaign, the phenomenological models were calibrated for microstructural evolution. In this case, we calibrated the typical JMAC mean field models, which are simple models, but could be interesting for the industry. And we calibrated static grain growth, dynamic recrystallization, and post-dynamic recrystallization models. Here you can see a comparison between the models and the experimental data. So after the models were calibrated, we jumped to the industrial case study. In this case, we collaborated with Ulma Forging Company, which is a forging company dedicated mainly to the oil and gas sector, which forges different materials. And in this case, we focused in the Inconel 625 welding neck flange. The methodology we followed was this one. First of all, we monitored the industrial process, then we analyzed the microstructure of the components, we simulated the process, and finally we compared the experimental and numerical results. In the process, it's like this. First, we hit the billet. We have a preform in the hydraulic press, intermediate heating, and the final shape is given in the hammer at high strain rate blows. After that, the component is water quenched. So we acquired different process data, the kinematics of the hydraulic press, and also it was interesting, the kinematics of the hammer, which was not easy due to the harsh industrial environment. That we employed high-speed camera and also a wire sensor, and we were able to experimentally acquire the counter blow speed and also the interblow time. This was really important to use them as input parameters for the simulations. After the components were manufactured, we sectioned them to analyze the microstructure, that is to say, the fraction and the recrystallized grain size at the end. So we performed 2D axisymmetric implicit simulations in the force simulation software using the real industrial data as boundary conditions and the Inconel 625 material file we developed. And finally, here you can see the results, in which we obtain very accurate results, especially at the recrystallized fraction. We obtain quite a good agreement. And in the case of the recrystallized grain size, we observe in some cases that we have a very good correlation with the numerical results, and in some cases we don't have so much accuracy. This, bear in mind that the JMAC models are quite simple models, that they are good for simple deformations, but they lack the accuracy in multi-step complex processes. That's why after the PhD, we developed more complex recrystallized models to improve and optimize the result. Finally, the conclusions. We developed the automatic thermomechanical tester, which was valid for testing under low and also especially intermediate strain rates, also at high temperatures. Regarding Inconel 625 characterization, so we obtained the flow behavior under high temperatures and intermediate strain rates, and we observed that a strain hardening tendency. Regarding microstructural evolution, we saw a really fast dynamic recrystallization at intermediate strain rates. And what's really interesting, we observed that recrystallization occurs in faster than 1 second. Regarding or taking into account that it's a really fast process, that we were able to quench the samples really fast, so before 1 second, and we observed already dynamic recrystallization. Regarding the JMAC models, we observed that under controlled conditions, simple deformation, they are good, but at intermediate strain rates and complex processes, more complex or tailored conditions are recommended. Representative results were obtained in the industrial simulations, also some inaccuracies were observed, and it's accurate, the accurate monitoring of the industrial process, so it's critical for using as input in the simulations. So these are the contributions of the PhD, and I would like to thank the Basque government and the ULMA forging process for the economic and technical support, and also Transvalor, CEMEF, and NTNU for technical support. So that's all from my side. Thank you.